Hello ladies and gentlemen, we're going to do 6.2 today. We're going to be doing growth and decay problems involving our differential equations. So our objectives are that we're going to use separation of variables. We've already done this before, and then we're going to solve a differential equation. And then we're going to use exponential functions to model growth and decay. This part is basically a pre-calc review, and then later on we'll talk about a different type of growth and decay. So the first example that we're going to do says solve the differential equation. So you're going to be given that dy dx is 6 minus y. So remember the process is in differential equations, like things play together. So all the y's play together, all the x's play together. So I'm going to put this like this. I'm going to cross multiply so I get dy is 6 minus y dx. I'm going to divide so I get dy over 6 minus y is equal to dx. Now I can solve the differential equation by integrating both sides. And at this point, I think you'll be good to go, but I'll do this one just for posterity. I'm going to do u substitution, so I'm going to let my u equal 6 minus y. So my du is a negative dy. So I have to introduce the negative on this side. I'm going to come up here. So I have a negative 1 over u du. And then on the right-hand side, that's easy. It's just x plus c, right? When I integrate this side, I get a negative natural log absolute value u. And then I still get a plus c, but 1c is enough for one problem, okay? So then what I'm going to do is I'm going to put my u back in. So I have a negative natural log 6 minus y is x plus c. And then I'm going to do, except I think that's good. I'm going to take the negative over here. So I'm going to do 6 minus y is a negative x plus c. Now I'm going to go to exponent form. E to the negative x plus c is equal to, and then 6 minus y. And then remember we've talked about this before. I can write this as e to the negative x times e to the c, which would be 6 minus y. But e to the c is just a constant. So I'm going to get, on this side, ce to the negative x is 6 minus y, and when I solve for y, I get y is equal to 6 minus ce to the negative x. So that was a little bit entertaining. Okay, not too bad. All right, for the next example, I'm just going to go to another page because I think I'm going to run out of room. This one also says to solve the differential equation. And almost always when we solve our differential equations, we have to move our variables around, and then we integrate. I'm going to be given this time that y prime is x times 1 plus y. I'm going to rewrite the y prime, and I'm going to start over here, as dy dx is equal to x times 1 plus y. I'm going to move the dx and move the y. So I'll go across, sorry. So I'm going to get dy over 1 plus y is equal to x dx. When you're taking your exam, one of the things that you get credit for is splitting this up into dy dx. And sometimes you will get a whole point just for showing that you put your dy and dx on the opposite sides. And then oftentimes you get another point for the integration, but it's easy to get that 1 point. So now I'm going to do u substitution on the left. So my u is going to equal 1 plus y. My du is dy. So then my left-hand side becomes 1 over u du, and this is x to the second over 2 plus c. When I integrate the left-hand side, I get the natural log absolute value. I'm going to go ahead and substitute my u back in. And yes, I would get a constant on the left-hand side, but I'm just going to write one constant because a constant is a constant. Okay? Now we do like we did on the last problem. I go back to exponent form. So e to the x squared over 2 plus c is 1 plus y. Almost forgot the 1. And then I'm just going to go ahead and write this as c e to the x squared over 2. Because remember, I can split this up into e to the x squared over 2 times e to the c. But e to the c is still just a constant. So I'm just going to do this. Is equal to 1 plus y, and then I'm going to get y is equal to c e to the x squared over 2 minus 1. Alrighty, so that one wasn't too difficult. So now what we're going to do is we're going to go back and talk about growth and decay, because we haven't done that for a while. I don't know that we used growth and decay in Calc 1, I don't remember. So let's talk about this. There's a couple of different models that you can use for growth and decay. We have y is equal to a e to the k t. If k is greater than 0, meaning k is positive, then we're talking about growth. And if k is less than 0, then we have decay. The a is the initial amount of whatever you're growing or decaying, okay? Another slight variation of this was what we did in pre-calc, and I could write it like this, where this is my initial amount, b is my growth or decay rate, and then x is time, okay? So you can see the equation in lots of different ways. This is probably the one that's most commonly used from pre-calc. Well, now we want to talk about the calculus version, because it gets to be a little bit more entertaining. So we have y is equal to c e to the kt. All right, so in this case, c is the initial amount. Water bottle's in the way, scoot it over. And then k is my constant of proportionality, which is really just your rate of growth, right? So I can do a proof, but I think I'm going to skip the proof. It really doesn't matter. There's really not any difference between these two formulas. I could prove the formula for you, but I think at this point that I'm not going to. I think just in the interest of time, we're going to use our formulas. All right, so the first rate, I didn't write the first example down. Oh, bummer. Now you have to write an example down. So the first example says the rate of change of y is proportional to y, and then when t is equal to 0, y is equal to 2, and when time is equal to 2, y is equal to 4. So it says what is the value of y when, I'm scribbling, sorry, t equals 3. Hopefully you can read most of that. So if I write as I read, it says the rate of change, so I'm going to write dy dx is equal to, is proportional to, so there's always a constant of proportionality, times y. And then if I solve this differential equation by taking the dx over here, this is going to be what I didn't show you in the last example. I'm going to get this example, okay? The other thing that they've given me are two data points. I know 2 and 4, and then I know 0 and 2, and I want to know what happens when t is 3, okay? All right, so c is my initial value, and I don't know that, so I'm going to have to find it. So I use this information to find my initial value, okay? So I'm going to solve for k. So I'm going to do 4 is equal to CE I don't know what my k is, but I know that time is 2. And then I can write this equation, and I can say 2 is equal to CE to the 0k. Alrighty. And that just gets weird. Okay, so e to the 0 is 1, so I get c is equal to 2. Is that what I got in the long run? That's not what I got. C is equal to 2. That is what I got. Ooh, I like this one better. So I'm going to say c is equal to 2. I can get there from here, but I can use both equations, but this is just much simpler. So now my model becomes y is equal to 2 times e to the kt. Well, now what I need to do, oh, my bad. So what I'm going to do is I'm going to use, I haven't found k yet, so I need to find k. So now I'm going to use this point. So I'm going to use the information that I have. I have CE, we found this to be 2, and now I'm going to put k, and then I'm going to put my 2 in. So now I need to solve for k. And this is just simple logarithms. So 4 divided by 2 is 2, is equal to e to the 2k. I'm going to take the log of both sides. I'm going to come up here, and I'm going to do 2k. Natural log e is the natural log of 2. The natural log of e goes to 1. So k is equal to the natural log of 2 divided by 2. And if I wanted to round, I would get 0.347 for that answer. Well, now I know a complete model. So my model is y is equal to 2e to the 0.347t. You could also put in the natural log of 2 in this spot and get a much more precise answer. The question wanted to know what happened when time was equal to 3, so now I just substitute that in. So I'm going to do f of 3 is 2e to the 0.347 times 3, and I get that my solution is 5.657. Alrighty, so that wasn't so bad. Okay, the next problem that we're going to do is a half-life problem. And there's lots of different ways that you can manage half-life. So let me get my paper switched around. All right, so I've already written the example. So if you want, you can write that down. I'm going to go plug my computer in. Never mind, I'll do it later. It says its battery's going to die, so hopefully it won't go to sleep yet. Alrighty, so there's a couple of things that are important before we start this problem about half-life. One of the tricks that I remember is that when I have, for example, if I use the model y is equal to t, if you have a half-life, you divide the time by the half-life period. And this has always been helpful for me to remember, and I think it makes the problems a little easier. All right, so I have 10 grams of the plutonium isotope 239Pu, and it was released in the Chernobyl accident, and then how long will it take for the 10 grams to decay to 1 gram. So basically, in this one, I want to solve for time. All right, and I believe, I left off an important detail, the half-life of the 239 chemical is, that's a long time, 24,100 years. That's a little bit, wow. So now what I'm going to do is I'm just going to substitute everything into my equation, and I'm going to use this one because I think it makes half-life easier. So I'm going to write y is equal to, I have 10. My decay rate is a half. I don't know time. And I know that my half-life period is 24, I forgot the 1, okay? And I got an extra 0, not batting 1,000. So you can use the other formulas with half-life. This is just the one that I tend to use the most when I have to deal with half-life. So it says I want to know how long it takes to get to 1 gram. So I'm going to substitute the 1 gram in on the left, and then I'm going to solve for t. And again, I do that with logs. So I have to get rid of the 10 first. So 1 divided by 10 is 1/2. raised to the t divided by 24/100. Gosh, I keep wanting to put an extra 0 in. Take the natural log of both sides. So t over 24, natural log 1/2 is the natural log of 1 over 10. And then t is equal to, I'm going to put the 24 up here and the natural log 1/2 down here. Okay, so I got rid of those guys. And then when you do that math to see if I have the actual answer, ooh, it's 80,059.285 years. That's an overwhelming statement. Alrighty, so that was a nice, easy problem. I have one more example for us, and we're going to talk about fruit flies. Oh boy, and if you'll remember when you were in my pre-calc class, we talked about fruit flies a lot. So in this particular problem, I have an experimental population of fruit flies, 100 after 2 days, 300 after 4 days. That's disgusting. How many flies in the initial population? So in this one, I'm going to use y is equal to CE to the KT, and I have two data points. I have 2 and 300. Sorry, I couldn't read. And then I have, oh, I got my numbers mixed up. Sorry. There were 100 flies after 2 days, right? There's my 100 flies, and then 300 flies after 4 days. Alrighty, now we're rocking and rolling. So if I substitute everything into the equation that I have y is equal to CE, right? My K I don't know, my time is 2, and I'm going to put in my 100. And then in the second data point, I have 300 is equal to CE to the 4K. I'm going to solve both equations for C. So C is equal to 100 divided by e to the 2K, and C is equal to 300 divided by e to the 4K. Both of the C's are equal, so 100 over e to the 2K is equal to 300 over e to the 4K. And if you cross multiply and put everything in the right place, I get 100 e to the 4K is equal to e to the 2K and 300. So I get e to the 4K over e to the 2K is equal to 300 over 100. Well, that's easy. And so I get, sorry, I'm kind of jumping all around. Let me move it up. E to the 2K is equal to 3, because laws of exponents say that I subtract. Take the natural logs of both sides. 2K natural log e, which goes to 1, is the natural log of 3. K is equal to the natural log of 3 divided by 2, which is about 0.5493. Well, the only thing I have left to solve for at this point is C, and I'm going to use that equation. So C is equal to 100 divided by e to the 2 times the 0.5493. And when I do that, I get C is equal to a decimal, so I'm going to round it up to a whole fly. Blech. So there's my whole fly. Alrighty, and then it says how many flies were in the initial population. So I'm going to say y of 0 is approximately equal to 33 flies. Phew! That was a lot of work just to find the number of flies. That's it for today. I will see you soon.